Hello everyone, welcome to Brain Blitz Audios. Today, in another episode of Mind Maps, we'll be dealing with the fifth chapter in physics of grade 12 CBSE. The chapter that we'll be dealing with is Magnetism and Matter, and as always, we're enlisting the help of a mind map to explain the chapter. Mind maps are really easy tools in order to make last-minute revisions. However, like this one, they can be very extensive. So this video is devoted to explaining this mind map in some detail so that you can find it easier. So today our chapter is Magnetism and Matter. So we know matter as something that occupies mass and space, that has mass and occupies space. But what is magnetism? Well, magnetism is simply defined as the phenomenon due to which certain substances attract steel, iron, nickel, etc. These are ferromagnetic materials. But more on that later. So today we'll be dealing with, first of all, a bar magnet, which is one of the most useful tools that mankind had ever discovered. And we'll be looking at magnetic field intensity, potential energy of a field magnet system, torque, and thermal power, etc. Then we'll be looking at magnetic field lines, dipole moment of circular loop, revolving electron, and solenoid. Then we'll be looking at some magnetic terms such as magnetic intensity, magnetic permeability, magnetic susceptibility, intensity of magnetization, time period oscillating of a bar magnet, etc. Then we'll be looking at the Earth's magnetic field, particularly the declination, the inclination or dip, which is represented as delta, and the horizontal component. Finally, we'll look at some magnetic substances such as paramagnetic, ferromagnetic, and diamagnetic. And finally, we wrap up this chapter using electromagnets. So let's start off this episode with our very first topic, bar magnets. So we've known bar magnets for a long time now, but what exactly is a bar magnet? Well, a bar magnet is a rectangular piece of metal, preferably iron, nickel, or cobalt. These are known as ferromagnetic, and they show permanent magnetic properties. So once a magnet, always a magnet, unless you put in some very heavy forces, that is. So bar magnets are usually permanent. They stick around, they have their magnetic property, and then they do not lose it, unlike electromagnets. Now, a bar magnet is shaped rectangularly, and it has two poles, one north and one south. And each of these has a pole strength, which is represented as small m, but more on that later. And as with all magnetic substances, a bar magnet also has an area around it where its magnetic force is effective, which is known as the magnetic field. And when it comes to the intensity of this magnetic field, we can compare the bar magnet with an electric dipole, which we have studied in our first chapter. In our first chapter, we've studied formulae for calculating the intensity of electric field on an electric dipole. Here we're going to be looking at intensity of magnetic field on a bar magnet. First of all, the end-to-end end-on-end position, which is also known as axial. Well, axially, we have the formula mu naught by 4 pi times 2m by d cubed. So the bar magnet is spaced like this, and a point P is present on the axis of the two poles of a bar magnet. The magnetic length is measured as 2L, and the distance between the point and the south pole of the magnet, the furthest one, is D. So if we take this equation and substitute mu naught as 1 by epsilon naught, and we substitute the value of m for P, then we'll get this equation as 1 by 4 pi epsilon naught 2p by d cubed. Now, this is the exact same formula for the electric field, for the electric field intensity at an axial position to an electric dipole. So Now we know that a bar magnet can be easily compared with an electric dipole. The capital M here represents magnetic moment, which is represented as 2L times M. So M times 2L. 2L is the distance here, and M is the pole strength, which we can partially think of as charges, but magnetically. Now, the next position is broadside. Now, this is close enough to our equatorial position for an electric dipole. So for broadside position, the magnetic field at a point P is given as mu naught by 4 pi times m divided by d squared plus l squared raised to 3 by 2. Again, when we substitute, we'll get 1 by 4 pi epsilon naught P divided by d squared plus l squared, the whole raised to 3 by 2. And when we take the distance between them, which is d, way greater than the length L of the magnet, then we'll get the formula 1 by 4 pi epsilon naught P divided by d cubed. Now that is similar for the equatorial position, the magnetic field, the electric field intensity of an electric dipole at its equatorial position. So the magnetic field intensity for a bar magnet at its broadside position at a point on its equator, which is far away from the magnet, is given by the formula for mu naught by 4 pi, the constant called permeability in free space, times m, which is the magnetic moment, divided by d squared plus l squared raised to 3 by 2. So these are the two ways in which we can compare a bar magnet with an electric dipole. So if we take a bar magnet in a magnetic field and we keep it at an angle, so the magnetic moment acts in this direction and the magnetic field B acts in the horizontal direction. So we have an angle theta in between. And so we need to find the value of torque, which is also known as couple. So that means there'll be two forces acting on the bar magnet like this. So one perpendicularly upward and the other perpendicularly downward, which rotates the magnetic field. So since the couple acts perpendicularly from the magnetic field and the magnetic moment, we've written the value for torque as m cross b. Now, m bar is the vector for magnetic moment, b bar is the vector for magnetic field, and the value of torque will be equal to m bar cross b bar, which can also be written as mb sine theta. This is due to the law on cross products. And once again, the magnetic moment here can be represented as m times 2L, and which is pole strength times the magnetic distance. And B here represents the magnetic field in which the bar magnet is present. So this is how we can find torque. Now, suppose in this scenario, the bar magnet moves by a further angle, a short angle d theta, and you need to find the work done. So the work done there will be dW is equal to torque times d theta. And torque is mb sine theta times d theta. So the total work done, it'll be equal to mb times integral of sine theta times d theta, which gives us the formula for potential energy as minus mb cos theta. Again, since cos theta is usually present in dot products, we can write it as minus m bar dot b bar. So we take, in this scenario, we take potential energy at theta is equal to 90 to be 0 because cos 90 is equal to 1. And that is the lowest part. So this is all about the bar magnet, and the bar magnet has a lot of comparisons with the electric dipole in the way of its torque and its potential energy and its magnetic field intensity. Now let's move on to a topic which is very important. It's known as magnetic field lines, and these are the way in which we represent the area of the effect of magnetic force around a magnetic object, say a bar magnet. So what are exactly magnetic field lines? These are imaginary curves whose tangent at any point gives the direction of magnetic field B. So magnetic field lines are continuous imaginary lines which represent the direction of the magnetic field. So magnetic fields, unlike electric fields, are closed continuous loop. They start from the North Pole and then they move on until they reach the South Pole. So outside the magnet, they move from north to south, the magnetic field lines, and inside the magnet, it goes from south to north. And the one of the most important properties that unite both magnetic field lines and electric field lines is the fact that they cannot intersect. Because if you do intersect, then at this point, there'll be two tangents, one tangent this way and the other tangent that way. So that means at this point, there'll be two directions for the magnetic field, which is impossible. So therefore, magnetic field lines, like their electric counterparts, do not intersect, and they cannot intersect. So when it comes to magnetic field lines, we put in more field lines to represent greater magnetic field. And so therefore, it's suppose in this plate, if we have a greater amount of magnetic field lines, this implies that there's a greater amount of magnetic field. So that is all about magnetic field lines. Let's look at another important topic, the dipole moment. The dipole moment is the strength of the polarity of a system of charges. In this case, instead of charges, we use the poles. So in this case, the north and the south pole. So dipole moment is the strength of polarity of the system of poles, which is a magnet. So when it comes to a solenoid, and when it comes to every other figure, the dipole moment has a general formula. This is represented by mu is equal to I times A, current times area. So when it comes to a solenoid has n amount of turns, and each turn has an area A, and the current I is passing through the whole solenoid. So in order to find out the effective dipole moment, we need to multiply the dipole moment obtained at each turn times n. So the value for mu in a solenoid will be NIA, where n is the number of turns, I is the current, A is the area of cross-section of the turn. When it comes to a single circular loop, a single circular loop has area pi r square, and this pi r square carries a current I. And basically, it is a collection of collection of various dipoles, or basically one dipole which rotates about its axis. So we can basically replace the current loop by a dipole, and this dipole has the magnetic moment as m times d, which is also equal to I times A. M stands for pole strength, and D stands for the separation between the two poles. So that's how we can find out the dipole moment of a circular loop. Since the circular loop has a lot of diameters passing through its center, so we can just basically think of it as one dipole rotating about its center. So hence we can find the dipole moment. When it comes to an electron, which is revolving in a circular orbit, we use the same formula, mu is equal to I times A. However, here we use I is equal to charge Okay, let's go back. We use the formula current is equal to charge by time. And charge of an electron is E, and the time taken, and the time is 2 pi r by V, but since it's inverse, so we'll write it as V by 2 pi r. So we have EV by 2 pi r representing current, and pi r square is the area of the circle which the electron rotates. So EV by 2 pi r times pi r squared, so pi gets canceled, one of the r's gets canceled, so we have EVR by 2 as the value of mu in modulus. So modulus means that it's the scalar value without direction. Now mu can also be written as the angular momentum times charge by mass ratio. So that is equal to mu is equal to minus E by 2 times me into L bar. And using the formula for the circular loop, where we considered the circular loop as a set of dipoles, we can use mu is equal to md also as a formula for finding the dipole moment of a revolving electron. So once again, the quantities. Small m stands for magnetic charge or pole strength. D stands for separation between the poles. R stands for radius of the circular orbit. E stands for the charge on the electron. V stands for speed of the electron. L stands for angular momentum. And me stands for mass of the electron. So that's why this becomes half of the mass by charge, the charge by mass ratio. Now, let's move on towards some magnetic terms. Now, in this chapter, there are a lot of quantities which are constants, and so therefore, it's good to know some of these magnetic terms. First up, we have magnetic intensity. What exactly is magnetic intensity? Well, magnetic intensity is the degree to which a field can magnetize a material. That is referred to as magnetic intensity, and it is represented by H, and it has the formula H is equal to B naught divided by mu, where B naught stands for the magnetic field and mu stands for dipole moment, which is also known as magnetic permeability. Now, we've learned about magnetic intensity, but over here we see that there is another quantity which is called intensity of magnetization. In case you're wondering if they're the same, no, they're not. Intensity of magnetization refers to the magnetic moment per unit volume of the material. So it's magnetic moment divided by volume. And magnetic moment is represented by m, which is equal to small m times 2L. So intensity of magnetization, which is represented by I, has the formula m divided by v, because its definition is magnetic moment per unit volume of a material. Now, time period of oscillating bar magnet. Now, suppose we have a bar magnet like this, and it has a couple, sort of. So it moves in simple harmonic motion. So first it rotates like this, and then because of the magnetic field, it starts rotating the other way. So now it starts to rotate about its center like this, given in the figure. So the time period for this motion is given by the formula 2 pi times root of I by mb. So this is similar to 2 pi root of L by G. Now let's look at magnetic susceptibility. So what is magnetic susceptibility? Now this is referred to as the ratio between intensity of magnetization and magnetic intensity. So it is just basically intensity of magnetization divided by magnetic intensity. And that's why the formula for Xi, which is the symbol for magnetic susceptibility, is I divided by H. Now, the last term here is known as magnetic permeability. Now, what is magnetic permeability? Now, permeability means the ability of a material to permit the passage of magnetic lines of force. That is the definition for magnetic permeability. And it is represented by mu, so it's also known as a dipole moment. And using the formula for magnetic intensity, we can write mu as the magnetic field divided by the magnetic intensity. So it is also related with susceptibility in the formula mu is equal to mu naught times 1 plus Xi m. Xi m stands for magnetic susceptibility of a magnetic material, and mu naught is very special because it stands for magnetic permeability of free space. And this is the same mu naught that we use in most of our formulas for magnetic relations. So we use the constant, permeability constant, mu naught divided by 4 pi. Now, point of fact, the value for mu naught itself is 4 pi into 10 raised to minus 7. So if you have mu naught by 4 pi, just equate it to 10 raised to minus 7. Now, let's move on to one of the biggest magnets that we know of, which is the Earth. You might not think of the Earth as a magnetic material, but if you've seen the functioning of compasses, then you would know that the Earth also exhibits a magnetic field. Earth is a natural source of magnetic field. However, we know that so far, using a bar magnet, the field lines go from north to south. So does the Earth have a big bar magnet like this? Not really, because if the Earth had a huge bar magnet, it would melt because of the huge temperatures at the outer and inner core. So how does the Earth produce its magnetic field? Well, the Earth's magnetic field, it is produced by convection of iron, nickel, and cobalt, which is present in the outer core. So they move about in the outer core, and that movement creates the Earth's magnetic field, which also has a very important, function in order to protect us from ultraviolet rays and other radiation coming from the sun. So the Earth also has a magnetic north and a magnetic south. And that's why the compass points north, because it is attracted towards the North Pole, the magnetic North Pole of the Earth. And the South Pole here attracts to the magnetic South Pole of the Earth. And that's why the name is referred to as north and south. On regular conditions, you would notice that a bar magnet, its North Pole, gets attracted to another bar magnet, South Pole. So technically, since the magnetic field lines of the Earth go in at the magnetic north, it's actually south. It functions as a south pole, while the magnetic south functions as a north pole. However, the naming condition that we use in order to name the two magnetic poles is dependent on the way we see it in a compass. So in a compass, the magnetic needle's north pole points north, so therefore we consider this as a north pole instead of a south pole. That's why the other side became a south pole instead of a north pole. When it comes to the axis of the magnetic field, it is quite different from the geographical axis. Because if you see, if this is the Earth, and let's say we have a geographical axis, so geographical north and geographical south, the magnetic field does not correspond to this same axis. It deviates even further. So this axis gives you magnetic north, and that axis, that part of the axis gives you magnetic south. So there's still a difference in angle between the two axes. So therefore, while the geographical north and geographical south produce their own meridians like these, the magnetic north and magnetic south also produce a separate set of meridian. So they produce their own magnetic field lines, similar to longitude, which we find on the geographical axis between the north and south. Once again, all of these are just imaginary. And that's why there is huge discussion on declination and inclination. So these are basically the difference in angles. Declination refers to the angle between the magnetic meridian and the geographical meridian. So as you can see, this is the geographical meridian. Let's say it's straight, and we have the magnetic meridian like this. So this angle here represents the angle of declination. So this is basically horizontal angular difference, angular displacement between the two axes. Now, what was our definition for magnetic field lines? Well, magnetic field lines are imaginary curves whose tangent gives you the whose tangent at any point gives you the direction of the magnetic field. So that's the same when it comes to the meridian, magnetic meridian of the Earth. So the magnetic meridian of the Earth, it also forms tangents at various points, and the tangent at a single point shows the magnetic field at that point. And this magnetic field, which say has a displacement theta, a displacement delta with the horizontal component, which points to the North Pole. This perspective here is ground perspective. So suppose the magnetic field of the horizontal component of the magnetic field goes along the ground, and this angle here represents the delta or the inclination, then we can define the angle of inclination or dip as the angle made by the Earth's magnetic field with the horizontal in the magnetic direction. So besides having a deviation from geographical north and geographical south, it also has a deviation as we move from the equator towards the poles. At the equator, the field line is straight and the tangent is also straight. However, as we move along, we find that there will be differences of angle delta as we move towards the poles. And over at the poles, it's just 90 degrees. Because the magnetic field, they move directly in there. And this is echoed in this statement. The angle of inclination at the equator is 0, while the angle of inclination at the poles, that is equal to 90 degrees. And that's why there is no horizontal component as you reach the magnetic north. When you reach the magnetic north, the compass starts spinning randomly. However, if you had a compass which shows you the angle of dip, then that would point 90 degrees. And that's why the angle of dip at the poles is 90 degrees. So we know that the magnetic field lines are curved around the Earth, and therefore there's always an angle of inclination between the Earth's magnetic field line and the horizontal direction of it. So once again, since it's B and then there's a BH, so, and there's an angle, say theta between them, so then we can calculate BH as B cos theta. again, we use the, you use the trigonometric ratios here. So this is, say this is the hypotenuse and this is the adjacent side. So then we can find the length of the adjacent side as cos theta times the hypotenuse. So BH will be equal to B cos theta. Now at the poles, theta is equal to 90 degrees. So therefore the BH is 0. And at equator, BH is equal to the magnetic field of the Earth, which is B. So that is how you measure the Earth's magnetic field. Now the Earth's magnetic field does not stay the same everywhere because in some places you can find quarries where the lodestone or magnetic materials are present. So there the magnetic field gets deviated. But what causes these magnetic substances? In general, there are three types of substances in terms of magnetic properties. Paramagnetism, ferromagnetism, and diamagnetism are the properties. So therefore, the substances are paramagnetic, ferromagnetic, and diamagnetic. When it comes to paramagnetic materials, these have a short tendency to increase the magnetic field due to magnetization. So suppose we're magnetizing it with a magnetic field, then paramagnetic materials tend to pull the magnetic field closer towards them. And due to this property, we can say that their magnetic susceptibility and the relative permeability to be greater than 1 because they tend to increase their magnetic field. Examples for materials with paramagnetism are aluminium and manganese. Now, we know that there are some materials like iron, cobalt, and nickel, which form permanent magnets. And these permanent magnets and the materials that make them are ferromagnetic. Now, what is ferromagnetic? Now, this is the tendency to form very, very strong magnetic fields through the material. So when a magnetic field is implied, there is formation of very strong magnetic field lines inside the given figure. And the reason why is due to the structure of ferromagnetic fields. So these have short particles, and these dipoles are having dipole moments each. However, in ferromagnetic materials, they are mostly arranged in groups called domains, and all of the magnetic moments inside a domain operate at a certain angle. So when the magnetic field is applied, most of the magnetic materials and dipoles, they tend to become in the direction of the magnetic field. Recall chapter number 2, where the electric dipole also rotated in order to be parallel with the electric field. Similar case happens here. So as these particles and dipoles began to become parallel with the magnetic field B, so this domain, one of the domains, will start becoming larger and larger. So therefore, there is a huge increase in the magnetic susceptibility and the relative permeability of these materials. And examples of these are Fe, Co, and Ni, and that's why they're used as magnetic materials. And that's why they have the tendency of strong magnetization in the direction of magnetic field. The third type of magnetic substance given is diamagnetism. So in diamagnetic substances, there is a tendency to magnetize the object. However, the direction is opposite. So these move in the opposite direction due to the fact that when a magnetic field is passed through it, the field lines tend to be pushed away from the object. So the diamagnetic object, it pushes the magnetic field away. So the tendency of magnetization in a diamagnetic substance is towards the opposite direction. Now, for these scenarios, the magnetic susceptibility, Xi, and the relative permeability, mu r, are less than 1. So both of these quantities are less than 1 for elements such as bismuth, copper, mercury, and sometimes nickel. Now, ferromagnetic substances can be converted into paramagnetic substances when we heat them at high temperatures. And at temperatures above a certain temperature known as Curie temperature, we can observe the change in property from ferromagnetic to paramagnetic. So that completes our study of magnetic substances. So magnetic substances form permanent magnets. However, ever since Maxwell proved that electricity and magnetism are united, there has been tremendous exploration of electromagnets. So unlike a permanent magnet, which stays the same forever, an electromagnet is a magnet in which the magnetic field is produced by an electric current. This magnetic field disappears when the current that produces it is turned off. So because of these phenomena, electromagnets have variable power. So as you increase the strength of the current, the electromagnet becomes stronger. And as you decrease the current, the electromagnet becomes weaker. Electromagnets can also be changed by putting a soft core of iron. The soft iron core has a high amount of magnetic susceptibility, so therefore it makes the electromagnet stronger. And electromagnets have a wide variety of uses. They're used in school bells, they're used as magnets in junkyards, etc. And the reason why electromagnets are used in these scenarios is that they can be turned off. So unlike a permanent magnet, we can turn off an electromagnet when not in use. So that means there's also the perspective of conservation. So we can switch it off when not in use and then put it on when you need it. And also, since a permanent magnet has a constant amount of magnetic susceptibility and magnetic field, it sometimes is very useful, but sometimes is rendered useless. But an electromagnet, however, can be adjusted to fit the kind of requirement it wants. For example, for a bell, the strength of the electromagnet does not have to be very high. However, for the electromagnets used in junkyards, they have to be very powerful in order to lift up junk, such as cars and used parts, etc. So that is why electromagnets today are more in use. And when it comes to electromagnets and permanent magnets, there is this curve known as the hysteresis curve. So it is basically a curve which determines the amount of power loss when we start increasing the current with respect to the flux. So therefore, there is a change in magnetic field. So materials with high hysteresis graph are used as permanent magnets, and materials with low hysteresis graph are used as electromagnets, because electromagnets are usually powered on AC current, so they have to turn very fast. They have to change their magnetic state very fast. So a material with low hysteresis is preferable. For a permanent magnet, we need something that can last forever. So therefore, ferromagnetic materials like iron and cobalt are used because they have a high hysteresis graph. And that concludes the chapter Magnetism and Matter. We looked at a bar magnet and the magnetic field of a bar magnet in its broadside and end-on-end position. We also looked at magnetic field lines, dipole moment of a circular loop, revolving electron, and a solenoid. Then we looked at some magnetic terms such as intensity, magnetic intensity, intensity of magnetization, magnetic permeability, magnetic susceptibility, and time period of oscillating bar magnet. Then we looked at the Earth in general and its magnetic field. What are the amazing properties that this magnetic field has and how is it measured, and the various angles that are related to it, such as declination, which is its angular displacement from the geographical axis, and inclination, which is the angle between the magnetic field at a point given by the tangent and its horizontal component, BH. Then we looked at magnetic substances in general, such as paramagnetic, ferromagnetic, and diamagnetic substances. And finally, we looked at electromagnets, the usage of electromagnets, and why they're better than at times than permanent magnets. So that concludes this mind map. However, don't forget that we have a whole playlist of mind maps of CBSE chapters. So don't forget to click the link of the playlist in the description down below. And you can watch those videos at your leisure. For more useful and interesting content such as learn words, NEET preparation, etc., don't forget to subscribe to our channel, Brain Blitz Audios. So until the next webisode, take care, stay safe, bye-bye for now.